Hello, in today's video we're going to talk about some aerodynamic basics. We're going to introduce some basic equations when it comes to calculating lift, drag, and moment of the aircraft, and we're going to talk about what these variables mean, and at the end we're going to do an example problem. So starting with our three basic equations here for lift, drag, and moment, they all have this 1/2 rho infinity v infinity squared common for all these questions, and this equals q infinity, which is equal to our dynamic pressure. If you ever watch like a rocket launch, you'll hear this term max q. This means the maximum dynamic pressure that the rocket is going to experience. This could also probably be applied to planes, but maximum dynamic pressure, this is what they mean. Because at some point, so if you're a rocket and you're going up in altitude, as you go up in altitude, density, so this is altitude, density drops, but velocity, as you're going up in altitude, is also increasing exponentially. So at some point, the density and velocity reach a point where this is maximum, because you get high enough where the density drops off so much and the velocity doesn't make up for that. So you reach this max Q pretty quickly when your density is very high relatively to, obviously, when you get to outer space and there's no air density, and very high up in the atmosphere where there's very little. Now this S term that appears in all three of these equations is the plane form area. So this is the total area of basically the bottom of the wing, also including the bottom of the fuselage. So let's say we have our very basic wing here. This entire area, so the area S, so would be the chord length, which is C, times the wingspan equals that S, which is in the units of, meters squared or feet squared. So that's the plane form area. Now this, up here in the moment equation, we have this L term. This is a characteristic length. So for a wing here, an airfoil, L equals C. Okay, let's say you have a cylinder of some sort, and your free stream velocity is going this way. So V infinity, whenever you see an infinity term, subscript, that means free stream. So it's the velocity, that the wind is traveling. It's like perpendicular or parallel to your way of travel. It's going into the air. So for a circle like this, the diameter, D equals your L. So for a airfoil, the free stream velocity is going straight along this wing. So if we were flying, I'm very bad at drawing the planes here, but pretend this is our plane. Got our wing. Free stream velocity is going that way, straight into the plane. Now going back up to our equations here, now that we know what all of these terms mean, so density times velocity times the plane for area, and then these CD, CL, CM are our coefficients. So this would be CL equals the coefficient of lift of the entire wing. We could also rearrange these, and you can find this would be a lowercase CL, which equals L prime divided by Q infinity times C, or CD equals, this would be lowercase, my bad, CD equals D prime divided by Q infinity times C, and then CM equals M prime divided by Q infinity C squared. So this is the units for coefficient of lift, there is no units. It's a unitless value. Also, these coefficient of lift per unit span are also unitless because L prime would be newtons per meter. Q infinity, so let's do the units on our dynamic pressure. That would be kilograms per meter cubed times meter squared per second squared times meter grams meter per second squared, unitless. It's actually unitless. So you're just left with no units. Okay, because this kilograms meters per second squared equals newtons. So Newton over newtons cancel. You're left with nothing. All right. All right, so I'm going to do a quick example problem that covers a lot of these basic aerodynamic topics. So we want to calculate the coefficient of lift of this airplane at 10,000 meters. The plane's mass is 70,000 kilograms. It is cruising at, flying at speed is the Mach number is 0.85, and the planeform area is 125 meters squared. And we're going to assume steady flight. So that means that's assuming a couple things. It's assuming that the plane is just flying straight at a constant altitude. It's not descending, it's not climbing, and it's not accelerating or decelerating. It's not changing velocity. And we're also going to assume STP, which is standard temperature and pressure. So you can look in the back of your book at some tables or look up some tables, and it gives you the values for a bunch of different things at a given altitude, which we have. So the first thing I'm going to calculate is what's our velocity. So to calculate that, so we use the equation for Mach number, which equals V infinity divided by square root of gamma R T. So we can rearrange this to solve for velocity. So velocity equals the Mach number times square root of gamma RT. And this gamma RT is A, which equals the speed of sound at a given temperature. Because really, speed of sound is only really a function of your temperature. So calculate this. Mach number is 0.85. Square root of gamma for air is just 1.4. This R value is a gas constant for dry air, and that is 287. And the units on that are joules per kilogram Kelvin times temperature, which if you want to look that up in the back of the book, is 223.26 Kelvin. So pretty cold, given that 0 degrees Celsius is 273 Kelvin. So cold temperature. So then solving for this, and also let's go make sure quickly our units check out here. So we have, joules per kilogram Kelvin times Kelvin. Kelvins cancel. You're left with joules over kilogram. Our units for joules are kilograms meter squared per second squared divided by then kilogram. So this is our units for joules. Kilograms cancel. Perfect. And then when you take the square root of this, you're just left with meters per second, which is our units for velocity. So that all checks out. Plugging in our solving for this, we got 254.58 meters per second, which then, if you don't have an idea of how fast it is, if you want to calculate in miles per hour, just take 254.58 meters per second, do some dimensional analysis. You got 3,600 seconds in 1 hour, and then 1 mile is about 1,600 meters. Solving this is 569.486 miles per hour. So pretty fast. All right, so now that we have our velocity, we're going to use the standard units here. Now we can find our dynamic pressure, which is Q infinity, which equals 1/2 rho V infinity squared. So that equals 1/2. So our density at 10,000 meters, you can look this up, is 4.1351 times 10 to the negative 1. So kilograms per meter cubed. So it's like 0.4 kilograms per meter cubed, which makes sense because the density of air at sea level is about 1 kilograms per meter cubed. So as you go up in altitude, the density drops. So it's about 0.4. So it's about less than half the air density, which is pretty impressive. Times our velocity, which would be 254.58 meters per second, and then all of this squared. Solving for this, you have 13,399.99 kilograms per meter second squared, which is the units of pascals. So check our units here. Kilogram, you're left with that. Meter squared, meters, so you're left with 1 meter on the bottom, and then second squared. All right, so we're almost there. So what else do we need to calculate the coefficient of lift? So our coefficient of lift equation, I'll go up here, equals lift over Q infinity times S. So we need to find lift, okay? But what do we know? We know we're in steady flight and our mass is 70,000 kilograms. So pointing down, we know lift equals the weight. So what's our weight? So we have 70,000 kilograms going down times 9.8 meters per second squared. And that leaves us with, this equals 68,600 newtons, which then equals our weight. So this is our weight, which equals lift. So our coefficient of lift equals, finally, now we have all that, 68,600 newtons divided by our pascals, kilograms per meter second squared. And this is kilograms meters per second squared times meter squared. Oh, not sorry, this would then be 125 meters squared. All of this comes out to 0.410, and see if all our units cancel, which they should. So kilograms cancel, seconds cancel, meters, left with 1 meter on the bottom, meters cancel. 0.410 coefficient of lift.